Data-driven decision-making systems are increasingly employed to make consequential decisions for human subjects. Decisions made in this fashion may affect certain individuals or social groups negatively. This realization has recently spawned an active area of research into formalizing fairness for machine learning. Virtually all existing formulations of fairness focus on guaranteeing equality of some notion of benefit across different individuals or groups. For instance, equality of odds requires the equality of false positive and false negative rates across different groups. In essence, the debate so far has mostly revolved around identifying the right notion of benefit and a tractable mathematical formulation for equalizing it. The view of fairness as some form of equality is indeed an important consideration. However, we argue that equality is not the only factor that should be taken into account. We draw attention to two important yet largely overlooked aspects of evaluating fairness, namely risk and welfare considerations. The importance of these factors is perhaps best illustrated by a simple example. Suppose we have four decision-making models A, B, C, and D, each resulting in a different benefit distribution across five individuals. Suppose a decision maker is tasked with determining which one of these alternatives is ethically more desirable. From an inequality minimizing perspective, A is clearly more desirable than B. Note that both A and B result in the same total benefit of 4 and A distributed equally. Similarly, C is preferred to D. Notice, however, that by focusing on equality alone, A would be deemed more desirable than D. But there is an issue with this conclusion. Almost everyone, except for individual 1, who sees a negligible drop of less than 2% in their benefit, is significantly better off under D compared to A. In other words, even though D results in unequal benefits and it does not Pareto dominate A, collectively it results in higher welfare and lower risk, and therefore, both intuitively and from a rational point of view, it should be considered more desirable. With a similar reasoning, C should be considered more desirable than A. In light of this example and inspired by the long line of research on distributive justice in economics, we propose a natural family of measures for evaluating algorithmic fairness corresponding to the well-studied notions of cardinal social welfare. Our proposed measure indeed prefers A to B, C to D, and D to A. The convex formulation of our welfare-based measures of fairness allows us to integrate them as a constraint into any convex loss minimization pipeline. Our empirical analysis reveals interesting trade-offs between our proposal and prediction accuracy, group discrimination, and individual fairness. Furthermore, and perhaps most importantly, our work provides both heuristic justification and empirical evidence, suggesting that the lower bound on our measures often leads to bounded inequality in algorithmic outcomes, hence presenting the first computationally feasible mechanisms for bounding inequality. Thank you for your attention.